All right, so the next thing we're going to take a look at, kind of another variable, the fourth one we'll see here, is power. Okay, and electrical power, very, very common, right? So you lose power in a windstorm or something, and then your whole world is turned upside down. What exactly is power? Well, power is defined as the rate at which electrical energy is consumed or converted into another form. So that would be, in the form of heat, for example, or light. Okay, and that's what we take advantage of all the time, right? You get electrical energy coming into your house, and that's converted, whether it's heat or, to turn on your lights or to power your fridge or whatever. What you're doing there is using power, right? So we define that as that rate at which energy is consumed and or converted per unit time. So power, we have the symbol P here, and then the unit for power is the watt, W-A-T-T, which is abbreviated uppercase W. So power then is the units here, 1 watt is actually equal to 1 joule per second. Okay, and we can actually use that to derive the other relationships or the other variables that power is related to. So if you recall, back above, we had current in amps being equal to 1 coulomb per second. Okay, so if I take my coulomb per second and I multiply it by the voltage, so voltage is defined as joules per coulomb. Okay, so joules per coulomb. What I end up with now is that the coulombs cancel out, and I end up with, guess what, joules per second. So coulombs per second was the current I, and then joules per coulomb was the voltage V. So this is then equal to power. So power is just a product of the current times the voltage, right? That's mathematically now how we can relate power to a couple of the other variables that we've seen so far. Now, we also know that V is equal to I times R. So if I take this I times R and I substitute it in here for V, okay, then I end up with a new expression for power. Power will be equal to the current I times. Now V is I times R. Okay, so then I end up with power being equal to I squared R. So that's a new expression for power. We also know that that the voltage, I'm sorry, that the current I is equal to V over R. So if I take this expression for I and I substitute it in here for I, okay, then I end up with a slightly different expression as well. I get P is being equal to V over R times V. So that gives V squared over R. And that's equal to the power P. So I have two other ways to express power in terms of the other variables. Depending on what it is that I'm given, I can just substitute those in and solve for P, or I can rearrange it and solve for any of the other variables if I wanted to. Again, this is nothing more than just doing a little bit of algebra on the original P equals IV equation. So we have our three equations here. P equals IV. That relates power to current and voltage, and that's always going to be valid. We have our second and third ways to represent power in terms of resistance, and these are only going to be valid for when we have resistors involved. So a couple things kind of result from these simple mathematical relationships. And we can say, for example, that when the if the current increases or the voltage increases, right, then the power delivered is going to increase as well, right? So we can get that from this equation. So as the current increases or the voltage increases, the power then is going to go up, right? And that's because there's a direct relationship between those variables. Now, in the P equals V squared over R relationship, okay, so the second one, we can gain some more insights from that. And what this implies is that if the resistance is lowered and it's connected to a given voltage source, well, then the power delivered is going to increase as a result of that. Right? Because we have a number that's smaller, if you have a smaller resistance here, the denominator becomes smaller. Well, then if the voltage here is the same on top, that value for P is going to increase because we're dividing by a much smaller number. So the power delivered there is going to be much higher. And not only is it going to be much higher, it's going to be more than expected because V is actually squared in this case. So let's say, you know, that if you double the voltage to a 25-watt bulb, right, the power is going to nearly quadruple to about 100 watts. And that will cause it to burn out. If the bulb's resistance stayed the same, right, then the power would be exactly 100 watts, but usually the resistance changes as the temperature increases as a result of that. So there are things we can glean from these relationships just by simply making some deductive reasoning with the relationships involved. All right. The last thing we'll take a look at in this section is how power is rated in terms of how you're charged for electricity, and that usually, if you look at your electric bill, you know, the cost is determined by kilowatt hours, right? So what exactly is a kilowatt hour? Well, it's a unit of energy that's used to measure electricity consumption. And as the name suggests, okay, a kilowatt hour represents the amount of energy used when a device with a power rating of 1 kilowatt operates for 1 hour, right? So 1 kilowatt hour would be equal simply to the product of 1 kilowatt times 1 hour. Now remember, the kilo here means 1,000, right? Kilo of anything means 1,000. So kilowatt represents 1,000 watts, right? Regular watts. So for example, if you have a 100-watt light bulb that operates for 10 hours, the energy that you would consume for this particular bulb for that time would be as follows. So we need to convert our watts to kilowatts. All right, so that would be 100 watts. We can use the dimensional analysis for every 1 kilowatt. We have 1,000. So watts go away. 100 divided by 1,000 would be 0.1 kilowatts. And then we're going to multiply that by the hours in time. So that's 10 hours. So that's going to give us 1 kilowatt hour as the consumption there of energy for this particular thing, right? So, you think about how long you leave your light bulbs on at home, maybe from the time you go home to the time you go to bed, maybe 4 or 5 hours, probably, I don't know, maybe up to 8. But that's how much energy you're using. And obviously that's going to cost differently depending on the time of day or the part of the country that you're in, for instance. We can use that simple relationship to determine that unit of energy in kilowatt hours. All right, so the last thing we can do here is we can also kind of relate this energy consumption to units of energy that we've seen before. So if you think about a kilowatt hour and what that is, so relating kilowatt, so that's a lowercase k, kilowatt hour to an energy of or unit of energy that we've seen a lot of before, which is the joules. Okay, so if I had 1 kilowatt hour, all right, I know that for every hour, there's 60 minutes, and then for every minute, there are 60 seconds, right? So I end up here, my hours go away, my minutes go away. So I have 3,600, if I look at my units here, 3,600 kilowatts. And then seconds is my unit. And then if I want to convert my kilowatts to regular watts, I know that for every kilowatt, there's 1,000 watts. Kilowatts go away. So what I end up with now is 3,600,000 to 3, and then a watt, or sorry, seconds times watts would be my unit. All right, and then we also know from up here that power, P in watts, is a joule. 1 watt is 1 joule per second. So if I substitute that into my thing over here, let's say recall 1 watt is 1 joule per second. So if I take this, what a watt is, and stick it right here for W, I get 3,600,000 seconds times joules over seconds. Guess what? Seconds go away, and I end up with 3,600,000 joules as being equivalent to 1 kilowatt hour. So in terms of, a unit that you see all the time, which is your electric bill, and how it relates to a unit that we've talked about in our class, a unit of energy like joules, that's the relationship. We just derived that not by doing a whole lot of fancy stuff. We just converted some units from one to another. So a kilowatt hour, in other words, is nothing more than 3.6 times 10 to the 6, right? Or 3.6 million joules.